We have been confronted with theories so many times of people who said, now we understand everything. And my answer always has been, no, we don't. We don't understand everything about Hawking radiation. There are very many, very fundamental problems with it. This resonates a bit. Does it? Can you hear me well? Okay. I would like to explain in what sense there are still mysteries about it. Basically, what you want to know is to understand the behavior of a black hole in terms of the behavior of things happening locally in its near or in its horizon or its environment. We understand the basic properties of the vacuum state, or so we thought, and the question is how to translate that into basic properties of a black hole. What is the black hole's Schrödinger equation? And questions like this. And the thing that was disturbing me a lot was that we really don't understand how to do this particular translation, how to get the black hole properties, quantum properties, as precisely as the properties of a hydrogen atom, but now derived from properties of the vacuum and the fluctuations in and around that vacuum. So this is the problem. And now, being at this meeting, of course, the first subject that came to our mind to talk about is the backreaction of Hawking radiation, because Hawking particles not only carry away information from black holes, they actually also carry away mass and energy. And that must have an effect on the black hole itself. The black hole must lose mass and energy by emitting the particles. Exactly what kind of mechanism that is not totally clear from the standard calculations. In fact, there's some confusion about this, confusion that reach magnificent heights when people talk about the so-called firewall. The firewall, which is basically a negation, a denial of what general relativity is supposed to tell us. General relativity should tell us that if someone moves into a black hole, he or she would not see any effect from the Hawking particles, let alone a firewall. So if that happens, there's something basically wrong in our understanding. And this always has been my main theme. There's something basically wrong in our understanding of Hawking radiation. There's nothing wrong with Hawking's derivation, by the way. It's a perfectly valid and sound argument, or so it seems. Right? If you just follow the book, the argument seems to be just fine. But now, if you ask further questions, you hit upon very mysterious problems. But now you've seen that I have added a second title to my talk at a later, when I was preparing this thing, which is on the renormalizability of quantum gravity, which sounds like something completely different and unrelated to black hole issues. But that is not so. I'm going to argue that renormalizability of quantum gravity, what does it mean, first of all, to have a renormalizable theory of quantum gravity? Is that what we want? It will be what many people ask. And at first sight, I would say, no, we don't want just renormalizability. We want understanding. We want to have exactly right all the equations of the theory. And if that requires renormalization on the way, so be it. So asking about gravity to be renormalizable may not be the best possible question one can ask. I grant you all that, but I see that there is something interesting to be said about that topic. And that's why I want to briefly explain what one could say about renormalization of gravity. So I go back to the 1970s and earlier, when renormalization was a sort of magic word in quantum field theory. Which theories are renormalizable and which are not? If you think of Young-Mills theory, is that renormalizable? Those were questions that are very much at our minds. So not very surprisingly, when the standard model started to mature in the later 70s, the next question that was asked was, what about gravity? Should we also not renormalize that? And very quickly it was clear that gravity cannot so easily be renormalized because of things having the wrong dimension. The Newton constant has a dimensionality which is such that if you go to smaller distances, the forces seem to blow up in a way that cannot possibly be squared with the idea of having a renormalizable theory of gravity. But the theory I want to briefly touch upon is that the process by which the the weak interactions became a renormalizable theory is actually very interesting. The discovery of the renormalizable models of the weak interactions, or the electroweak interactions, could have taken place along a different route than it actually was. So I'm going to give a non-historical explanation as to how we could have discovered renormalizable theory of the electroweak force, starting off with a completely non-renormalizable theory that we had. And this is just the table of contents of what I'm briefly going to do, which is that in the ordinary Fermi interaction, which is what the theory started off with, the Fermi interaction saying that when two fermions meet each other at one point, two other fermions emerge. So altogether, 4 particles are involved, 2 particles come in, 2 different particles come out. And that's a 4-point interaction. And that interaction is fundamentally non-renormalizable. In that theory also, you will be able to introduce magnetic monopoles. Magnetic monopoles had been studied by Paul Dirac way back in the 1930s. And he already noticed that there's a quantization rule for magnetic monopoles, but the monopoles he studied were fundamentally singular. There was a singularity that you couldn't get rid of, a so-called Dirac string. Now, the claim is what could have been done, it wasn't done this way, but it could have been done this way, was you could have formulated the theory using auxiliary fields, and then look at the divergences, and then discover that there's something missing. When you discover something is missing, you cure the theory by adding the missing term to the Lagrangian, and lo and behold, you get a renormalizable theory. Not only that, but that renormalizable theory also contains pure magnetic charges, as the case may be, depending a little bit on further technical details that I won't go into. But those magnetic charges are again magnetic monopoles without any singularity. So now you get a theory that also contains monopoles without singularity. And the remarkable thing is that you can do the same thing for gravity, I claim. For gravity, we started the Einstein-Hilbert action, and just like we had for the electroweak theory, we discover it's hopelessly non-renormalizable. So what do you do? And also there are black holes, and black holes contain a horizon and a singularity. Now you add auxiliary fields, you discover the theory is divergent, you notice there's something missing, correct the theory for the missing terms, and then you get something that looks like renormalizable. And then again you look at this crazy soliton-like object called a black hole, you'll discover it's no longer singular. It doesn't even have a horizon anymore, it has no singularity, it seems just as regular as the magnetic monopole. And if that is the case, then the information problem should also go away. I say should, because this is something one has to check in a real calculation, which is very, very difficult. Now, let me explain now the electroweak theory a little bit more detail. So what was it before 1970? Before 1970, we had this 4 Fermi interaction. The way the interaction was described was to say that you have a fermion and current. The details of the current is not so important, but there were, it basically looked like this, and then you take the square of that current and you put that in your Lagrangian, and then you get a theory, and that theory is not renormalizable. So now what could have been done is, you see it here, 2 fermions come in, 2 fermions come out, and there's something happening here that you don't understand. That was the theory in those days. Then we could have said, well, let's introduce an auxiliary field, a vector field, which is an auxiliary field that comes associated with this vector current. But we rewrite the Lagrangian this way. We write a squared plus and then an expression which is only linear in the fermionic current. That has the promise of being a renormalizable theory, because now if this A has a correct dimension, then this thing has the correct dimension to be possibly renormalizable. This would bring us one step further towards a renormalizable theory, even though I did not change any of the mathematics. This Lagrangian is identical, it has the same physics as this one. And that's because you can integrate out the A mu field, find that A mu is just G times J mu, and then when you plug it back in, you again get this Lagrangian. So nothing happened. You can recover this Lagrangian by just this auxiliary field. Physically nothing happened. Mathematically the whole thing looks different than what it was before. You could do the same thing to get the masses and other symmetry breaking features of the electroweak theory in their place. And that is by adding another scalar field. Mind you, this is not how it went historically. Sometimes people introduce scalar fields which do a job like this. So they're called schizoon, which is they break things without doing anything else physically. So a schizoon field is introduced, which you could give a self-interaction like this, which means that the field will have the value f in some direction, and then instead of a mu squared, you write a mu squared phi squared. And this was only in order to enhance the internal symmetry of the theory. So you wanted a local symmetry. Why do you want that? That is just a guess. This is actually the reason why historically things did not go this way. People could not have guessed that this was the right way to add more auxiliary fields in the theory. But this phi field could also explain all the fermionic masses which do not obey the local symmetry by just coupling those fermions again to the phi field. Well, this would have been good for nothing. If someone wanted to publish a paper with just this proposal, the paper would probably have been rejected because no new physics is revealed by this procedure. But mathematically, you can do something. You can ask for what is the divergences of the theory. Why is a theory not renormalizable? And the answer was, if you take closed loops of those fermions, by the way, the theory at this point only contained fermions as dynamical variables. So if the fermions go into a closed loop, diagrammatically, you get the first quantum corrections. You find that all Feynman diagrams containing these fermion loops are highly divergent. And if I now only need to know the fermion loop with two of these auxiliary A fields, you find that divergence goes like k squared, a squared. And also, the scalar field would have k squared times phi squared, and there could even be a diagram like this, two phi fields and an a field. So all these diagrams are basically fundamentally divergent. So the only thing you had to say is now it looks like a minor step, but it would have been a gigantic step if people had actually done this historically this way. The step would be, well, if these terms are needed as counter terms, let's put them in the Lagrangian all from the beginning. So let's add a term which has this symmetry structure. It turns out to be the Young-Mills Lagrangian. Why? Well, the theory has an internal local symmetry, so no other term could have come out than f nu squared. These would give rise to kinetic terms for the phi field, which up to now was just an auxiliary stationary field you could integrate away. But now you give it a kinetic term, now you can't integrate it away anymore. But actually, this d mu is going to be a covariant d mu, so it means that you get also diagrams of this form, just because the field phi is not invariant under the local symmetry. So now you see all those terms, which are now familiar in the standard model, the Young-Mills terms, the kinetic terms for the Higgs field, and the way the Higgs couples to the fermions, all that now in agreement with the local symmetry. And now you discover, by God, this theory is renormalizable. Why is it renormalizable? Well, all the counter terms that you need for the theory are already there in the original Lagrangian. But you have to realize that actually terms go away when k goes to 0. So now you understand why, if you only know the long distance behavior of the theory, you only know the theory, how it behaves when k is very small, now you can see why those terms did not sit in the original Fermi theory. Because we were working at too low energies. We didn't find the correct k dependence yet. So that's why those terms seem to disappear in the old Fermi theory, and now they are added as kinetic terms, and now you get the full standard model. This leads to the Young-Mills theory, of course, as I said, but actually to the entire standard model as well. This could have been a way we could have discovered the new renormalizer theory for the weak force. And now, my claim is, in principle, we can do the same thing for gravity and just see what happens. But again, you have to be very smart in guessing the right auxiliary fields, which at first will just be mathematical ingredients good for nothing. It looks like you had no good reason, no good physical reason to introduce those, but only mathematically it would make life easier. So the following attempt appears to be successful, and that is that take the Einstein-Hilbert action, add to it the meta-Lagrangian, and leave space for another addition to be added later. I call L kinetic, the kinetic term, today does not exist in our understanding of gravity. So this is going to be a new term. And the Einstein-Hilbert action is usual action. I add to that the cosmological constant, not so much because it has actually been observed that there is a tiny cosmological constant, but because it's very illustrative for what I'm going to say next. To have such a term also, I put that in the Einstein-Hilbert action. Then we also add the matter fields, but now we know exactly how to do that. We now know the standard model, so yes, we can add the standard model into actions, but we don't put here yet anything. And now we find that this theory also has a black hole, and the black hole has a horizon and a singularity. Something is not quite right, but that's mainly because we all know something is not quite right in quantum gravity. It's not the renormalizer theory. We do not understand its small distance structure sufficiently well. And now come the auxiliary fields, and this is a guess. Maybe someone else will do it in a different way. I do it this way, that I first extract out a totally useless field. You could call it a dilaton field. My way of adding a dilaton in the theory is by writing it as a square of something, omega squared. Other theorists put here an exponential function. You can do it any way you like, depending on what you want to do next. For me, it's very important to write here an omega squared. Then Lagrange depends on omega and g hat. Well, g hat is just whatever happens to the metric tensor if you pull out the factor. So altogether, this has a trivial local symmetry. That is, I can multiply g hat by a function capital omega squared. If I divide little omega with the capital omega the same way, of course the net effect of this transformation is completely nil, nothing, so it doesn't change any of the physics. But now I can also say my scalar fields and other fields have dimension, therefore they also scale with the factor omega. Then I have built in conformal symmetry in the theory. Again, if I would send this paper to a journal, they say, well, you've done nothing physically, so what is this good for? This is just only auxiliary fields. But it does add a new conformal symmetry to the theory. Omega actually defines sizes of things and scales of things. So the fields that we are familiar with in ordinary language are always the ratios of phi divided by omega, or psi divided by omega to the 3/2. Those are the fields that you normally use. Normally we never use the phi field separately and the psi field separately. Okay, now is the proposal, do this and see what happens. So, this changes a little bit the definition of sizes of things. That if you take out the omega field as just another conformal field, then sizes are the coordinate sizes, but they don't mean a thing. It's like having a relativity theory where you say there's an absolute velocity. No, there's no velocity anymore, you can just transform. Same thing now here with size. An absolute size doesn't exist anymore because you can transform everything along by making a conformal transformation in your coordinate frame. So, but if you do this, one striking thing happens. You can rewrite now the Einstein-Hilbert term of Lagrangian, and it becomes this. It becomes a beautiful kinetic term for the omega field. And that's why I wrote it as a square originally, because now you find that you get a ordinary looking kinetic term for the omega field. There is a term omega squared r hat, because you are using the g hat potential, which you also are familiar with when you take ordinary scalar fields. You also add a 1/12 r phi squared. You do that to make the theory behave in a canonical way under conformal transformations. This actually physically has very little significance, this term here, because on shell r vanishes anyway, so it doesn't change much of the properties of the theory. By the way, the cosmological constant here will carry a factor omega to the 4th. In a scalar field theory, you have a self-interaction also like phi to the 4th. It still will leave the theory renormalizable. So the one striking thing about this action is that you say, hey, this looks like a renormalizable theory. Omega, it just obeys a renormalized Lagrangian, somewhat unexpected, but this is the way it happens. And the other matter fields are renormalizable, so why is this theory not renormalizable? Well, because there's something missing. What is missing now is a kinetic term for the g hat field. G hat, the matter tensor with the conformal factor subtracted away from it, is still a dynamical field, but it has no dynamical term in the Lagrangian. That's why the theory doesn't make any sense, or rather, it does make sense because it's just a mathematical transformation of the theory that you're all familiar with. But there's something very odd about it. The kinetic term for the G-hat field is missing. In fact, what happened is, originally that was in the Einstein-Hilbert action, but the Einstein-Hilbert action, by this transformation, changed into a kinetic term for the omega field. If you look carefully, you find another difference between the omega field and the phi field. The phi field could be just a Higgs or any other scalar field in a standard model. The difference is the sign. The omega field comes with what looks like a wrong sign. It comes with plus signs here, whereas here you have minus signs. But this plus sign is crucial for the theory. It's not an anomaly, not a disease. Quite to the contrary, you just do this theory as if nothing happens and you find this is the right way to handle things. It does mean that in quantum mechanics, you might choose omega to be an imaginary field rather than real, which is rather strange, but if you do the function integral, you find that indeed a correct prescription is to take a complex contour for the integration, the function integration over omega, not a real contour. Then the integrals, the function integrals are completely nonsensical. You have to take a contour along the imaginary axis. But now, as for my program of constructing renormalizer theories, let's look at the divergent diagrams. And all the diagrams which are divergent are now diagrams which have G hat as their external lines. So G hat couples to the other fields, but G hat did not have a kinetic term. So what you find is these diagrams where the heavy wavy lines are the G hat metric tensor lines. These diagrams all diverge typically as a fourth power of the momentum, k to the fourth. And I write here delta G hat. I mean, if you take a variation in G hat, then these carry powers of G hat affect any power. It's nonlinear theory. And they all come with a factor k to the fourth. So now you ask, I have a theory with an enhanced internal symmetry. That is what my omega field was good for. It adds to the theory local conformal invariance. So now all these counterterms, whatever they must automatically be locally conformal invariant. Otherwise, the theory will be internally inconsistent. So the only local conformal invariant term that you can have is the while curvature squared. You cannot have I mu nu squared, not I squared, or any other combination except for the while combination, the C squared. And you know you can transform these, yes?
There will be an R squared term that you can write, just R, right, R omega hat. You use the phi compensator to make it conformally invariant. It will not be written entirely in terms of omega hat, but it will be conformally invariant.
I don't say.
Compensating field, so you can always write R squared in a conformally invariant fashion.
But we have to discuss this later because I'm a bit puzzled by that remark. But because Mike was saying more or less the same remark when I gave this talk earlier, that the strange thing is if you do this just by the book, then you find indeed that there are other terms, but I claim that if I would follow the rules according to, well, the book about symmetries, then I should expect all these diagrams to display internal conformal symmetry. So
Conformal symmetry, because you have a phi that can be used as a compensator, so you can always write anything in fact in a conformal fashion.
yes, except that I think I'm going to impose an extra condition on this theory, this omega here. I squared it, and that means that this is now a completely renormalizable action for this omega field, which is conformal. So there is internally, the only interactions that G hat is having with this other field is conformal invariant interactions. So I'm just looking at conformal invariant in terms of the G hat field, and well, as far as I understand, there should only be this term coming out. But we should leave this for discussion perhaps, whether it's obvious or not. Because the other terms which, oh no, it's continuing on the next slide, that, so my claim is if this theory would be worked out right, we should only get these terms. However, there are anomalies, and maybe, but we'll discuss that, what you talk about is a conformal anomaly. And the conformal anomalies are going to be a plague, but also interesting at the same time. So this is going to be a very important feature that we have to discuss in this theory. So this theory would become the fourth derivative of only the transverse components of G mu, and one can analyze what this interaction does. The expansion with respect to this coupling constant, which I put as a 1 over coupling constant here, just like you often do in Yang-Mills theory, then the kappa expansion is a more or less familiar perturbation expansion. So now I can consider this entirely as a perturbative theory, where I've looked at all the perturbatively renormalized terms you can have there. And now, we all also know what happens if you put fields in Lagrange which have k to the 4th in their propagator. Those fields are going to generate negative metric states. And this has been very much my concern. I'll postpone it for a moment, but this is related to the remark that Kelly just made, the 1 over omega squared. So if you do the thing that you talk about, and I had a discussion also with Michael here, you get d omega over omega terms and d omega over omega squared terms. If you look at the r squared and you plug in back what you call phi field, but I call that omega field, basically, the dilatant field, you get 1 over omega terms in your interactions. And those terms, to my mind, should be forbidden if omega is an ordinary scalar field. So if we forbid this, we say we must have a constraint on the theory. These terms should not appear. If they do appear, it's a conformal anomaly. We must demand conformal anomalies to be absent. I want conformal symmetry to be an exact symmetry. This also was actually was led to this idea from studying black holes. Then I come back to black holes and say that indeed and we should have exactly conformal invariant theories, not approximately conformal invariant theories, not conformal invariant theories which have conformal anomalies in them, because then I'm in deep trouble. So this is basically the consequence of an anomaly that we should try to remove from the theory, by brute force perhaps, but that also makes the theory interesting, by the way. If you're forced to change the model the way you thought it was, in order to rescue a symmetry, then maybe you learn about new physics. So it's this is where the whole theory becomes non-trivial, of course. And now, black holes, a decaying black hole has an information problem, and I tried to formulate this problem already before. That the problem is how to translate the behavior of a black hole in terms of physics of the vacuum surrounding the horizon, and how to derive for a black hole a meaningful Schrödinger equation. All these problems are there. So, for instance, there's a problem of the following sort, and this is a problem which I call the complementarity principle. I'll say why it's a principle, but first phrase it as a problem. The problem is if you have two observers looking at the decaying black hole. One observer goes into a black hole, will go right through the horizon as if nothing happened at the horizon. So that observer will definitely see that he is surrounded by the metric of a space-time, which is the metric of a Schwarzschild solution with a mass m, the same mass that he fell into. But the distant observer who sees that the black hole decays will also see that ingoing observer hovering around on the horizon, never getting through, but shrinking slowly while the black hole shrinks while emitting Hawking radiation. So eventually, the outside observer sees that the black hole is losing all its mass while the ingoing one is still going in. So, well, how important this problem is something, again, you can discuss. But I claim this is an important disagreement that two observers have about the mass of the black hole. And this I would like to resolve in terms of a principle called black hole complementarity. The idea is that both observers are right. They observe what they observe, and they deduce from that what will happen next with a black hole, but they're using different language. It's very much like in relativity theory, where the concept of electromagnetic fields change roles when you describe how a moving observer looks at electromagnetic fields. It's something very similar, that different observers look at sizes differently now, and what they really differ about is mostly the conformal factor. So the point I want to, yes, the difficulty arises when two observers disagree about the vacuum state. So one observer will say, no, it's going to be the Hartle-Hawking state, that's going to be my vacuum, and that's the ingoing observer who will claim that. But the observer says outside, says, no, no, that's not the vacuum state at all, that's a state which is full of Hawking particles. My vacuum state is what's called the Bowler vacuum state, and that is when I try to remove all the Hawking particles. I'll never succeed in doing that all the way, but that would be my vacuum state if I could remove these Hawking particles. Who is right here? And of course, it all depends on what your killing vector, your time vector is going to be. And so, in a way, they're both right, but they have a different definition of the vacuum state. And since they have a different definition of vacuum state, they have a different definition of vacuum expectation values of fields. So that is why the two observers will now disagree about the conformal factor. And roughly speaking, when you have a firewall, what will happen is that if two observers look at an atom, the other side of the firewall, one observer will think that the atom shrinks. And the other says, no, no, that doesn't shrink. I just had to perform a scale transformation to see the atom as at the same size as ordinary atoms. So who is right about this? Well, it's a question of choosing your coordinates right. So the theory is going to be complicated by the feature that you don't know absolute definition of sizes anymore. And that's what's the whole idea about conformal invariance. So for instance, what you can do is you can take the mass of a black hole. Yeah, I want to speed up a little bit. I see my time is running short. So the mass of the black hole could be made time dependent. In this way, I take the Schwarzschild metric with the mass removed. I put the mass as a term in front. This is a way you can rewrite the Schwarzschild metric, by the way. But now, the different observers have a different idea about the conformal factor in front. So one will say this m squared is a constant. The other says, no, it's a weakly time dependent. Since it is weakly time dependent, this is no longer a solution of the ordinary Einstein equations in vacuum. No, there are particles, and those are the Hawking particles, which either get out of the black hole, or other observers will actually see Hawking particles going into the black hole. So, again, another observer will say, no, those are the Hawking particles, that's a collapsing star you're looking at. That's going into the black hole. So they all disagree about what goes in and what goes out, and by that they disagree about this factor m in front. Because without factor m, you see nothing going into. With a factor m constant, you see nothing going in or out of the black hole. If m is time dependent, whatever way, you either see things going in or you see things coming out. So, so this would be a way to get that issue straight. And roughly what you see now is that with conformal symmetry active, you can describe the black hole. This would be the more or less conventional picture of black hole. It arises, it may emit Hawking particles, but it never reduce its size. That's wrong, of course. Hawking particles carry away energy and mass, so it should reduce in size. What picture is right? Well, my claim is this is what the outside observer would make out of it. The outside observer says, no, here a black hole is formed. The collapsing matter never really goes through the black hole. At least I don't see it going through the black hole. Eventually, collapsing matter will reach a point, but that's when the whole black hole has disappeared by Hawking radiation. So now you see that the Hawking radiating black hole looks more time reversal symmetric than the classical black hole. You also see in this picture, in a sense, the horizon disappeared, but if you look more carefully, also the singularity at the center also disappeared. It has been removed to the infinite future long after the black hole actually decayed, so the singularity really isn't there anymore. And the Penrose diagram then also starts to look like an ordinary Penrose diagram of the vacuum without any topologically non-trivial distortions. If you have a Penrose diagram like this, then the ingoing information and outgoing information will be related by ordinary S-matrix elements. So this should remove the information paradox. I say should because I haven't actually done the calculation. So, but this suggests that all these ingoing particles, the early particles, sorry, the outgoing particles, the early particles, and the late particles, all together form one single entangled quantum state. And in discussions about the firewall, this was an important theme. To what extent are these particles entangled with these particles? The answer is yes, they are entangled because all together they form one single state in Hilbert space. And if your pendulum is totally trivial, nothing disappears anymore, so there's no reason to think that this will be a density matrix or anything, because you've got the entire Hilbert space at your disposal to construct this state, which is not the vacuum state, because you did have a time non-invariant situation as a background. The background time is not the time that a local observer would use here, and therefore this state, which is a vacuum state for the local observer, is not the vacuum state for the late observer. That argument still holds. So you do see Hawking particles coming out, but you do see them coming out entangled in a single quantum state. Again, this is a formal answer and not yet a technical answer. The way you can look at conformal symmetry is also this. I think it's very interesting that actually the outside observer could see a black hole as something shrinking, but whatever is making up the matter which forms a black hole is not ordinary matter at all. It's dynamite. It contains explosive material, and all that explosive material explodes exactly at the right moment. The distant observer will not actually see the explosion. He will see it very, very strongly redshifted. So strongly that the only thing you see coming out of the explosion is Hawking particles. So here are the Hawking particles that the outside observer sees coming out. The local observer will then say, no, this is an explosion. But someone who goes with this stuff into the black hole will disagree, because he says, I cannot possibly imagine who set the fuse here so precisely that the explosion took place exactly at the right moment. And actually, the observer will not see any explosion at all, but see the thing continue to a singularity. So now you say, well, this is a conformal transformation. From the picture where this matter continues to form singularity to the picture where the matter actually explodes to make outgoing particles, that is just a conformal transformation. A space-time transformation which affects the composition of matter as well as space and time. So it's a very complicated transformation which you have to work out. By the way, this requires baryon number violation, because if these are baryons, there's no way to make them all explode. The standard model contains baryon number violation in a very subtle way, but so it's not impossible. But now you have to say how that all that can be used here to make the thing hang together properly. So now you see that features of the standard model, of which the origin was somewhat obscure, now become very, very essential. We cannot have conservation laws that would prevent this explosion to take place. So you see, you are going to have very strong demands on the composition of the matter part of the Lagrangian. It's not free in this theory. So it now looks as if the black hole became regular, and that is, again, what this theory has in common with the electroweak theory, where you now suddenly, with all the renormalized Lagrangians, you can make a magnetic monopole that is locally regular. Oh yes, non-conserving forces. So I want to save time a little bit, so I just say a few words what this says. The standard model cannot be chosen to be anything you like. The matter Lagrangian must be very, very special. It must be such that if you perform these transformations, you get a theory which is entirely conformal invariant. That is not automatically the case. A theory which is like the standard model, if you remove all the masses, you don't get a conformal invariant theory, because the theory will be full of anomalies. In fact, all the Cullen-Simancic beta functions express different conformal anomalies in the theories. All these beta functions in the new formalism should vanish, which means that all the parameters in the standard model should be at their fixed points, which also means everything should be calculable in the standard model. And this is one exciting thing about this theory. It makes the standard model such that everything should, in principle, be calculable. Now I left for the last the problem of the negative metric, because there was a wrong sign in the omega field, but worse even, I had a k to the fourth propagator. And that sign is a sign in all the quantum field theory that cannot be right. If you have a 1 over k to the fourth, you can actually disentangle that and having two poles. It's 1 over k to the fourth in your propagator is obtained if you take the difference between two poles, a 1 over k squared pole and a 1 over k squared plus m squared pole. So I investigated this Weil curvature squared action to find out that action actually describes particles of two kinds. One is the ordinary graviton. It's still there, 1 over k squared potential. It has correct metrics, so the graviton is a physically acceptable particle. But besides that, it has this funny pole. And then I investigated that funny pole, 1 over k squared plus m squared pole with the wrong sign, and looked at its helicity of the fields associated with it. I found helicity plus or minus 2, helicity plus or minus 1, and a single field with helicity 0. And then I investigated the poles, they're all on the same pole, m squared. And I said, of course it is. This is a massive spin 2 particle. It's a massive companion of the graviton, which I decided to call gravitello, just because gravitino means something else. So it's related to the graviton, so I call it gravitello as a partner of the graviton, which is a heavy spin 2 particle, which therefore has 5 components. But altogether, this makes the theory apparently work, except for this awkward minus sign. The minus sign means that the particles produce either negative probabilities or it contributes negatively to the total energy. These two interpretations of the minus sign are interchangeable. You can say either it's an object with negative energy or it's an object with negative probability. If you look carefully, you find that this is basically is the same thing that you're saying in somewhat different words. Now, the claim is that this might have a natural explanation in the theory of quantum gravity. Natural explanation is that Einstein's equations are obtained by saying that G mu is related to T mu matter, but G mu is also actually the energy momentum tensor of the omega field. That's the Einstein tensor T mu. So when you say G mu equals T mu, you say T mu of matter minus T mu of the omega field is 0. The minus sign comes because omega field has a wrong sign, remember? So that is negative energy momentum tensor. The Einstein equations has basically 10 components, out of which 4 are just natural consequences of coordinate reparameterization invariance. So basically 6 independent equations. And now I say, look here, the T mu of matter was originally related to the G mu of Einstein, but the G mu is a G mu of a single field, with only 1 degree of freedom. I need 5 more degrees of freedom to add up to this 6-component situation here. So I think the gravitello also has the wrong sign because it has the hook at the right-hand side of Einstein's equation, not the left-hand side. So the left-hand side is something which obeys a conservation law, just like the right-hand side does. And so, so if you interpret the gravitello as part of the gravitational field, its wrong sign is as acceptable as the wrong sign is for this omega field. Now, this is somewhat mysterious, and I'm not sure this is the right interpretation, so this could be, again, something for discussion, whether this is sufficient to say. Normally speaking, when you have a negative metric, your theory is in a very bad shape. So whether it can be cured this way at all is something that has to remain to be seen. Just a few words. You may have heard about the so-called asymptotic safety theory of gravity, which is a theory that the gravitation forms a non-trivial fixed point in the ultraviolet, so that you get an effective theory for gravity where you have an ultraviolet fixed point. The theory I've been proposing is not that different. Here also you have internally a sort of conformal invariance near this point here. So this is a conformal invariant theory, somewhat related to the theory I've been proposing. I claim that the gravitello with its wrong metric might be the same disease which could also emerge here in the form of Gribov, of Landau ghosts. The Landau ghost is apparent unphysical excitation that theory can have when you have an ultraviolet fixed point. So you have to be very careful whether these theories are internally consistent or not. I think I have the same problems as these theories which use asymptotic safety. The difference is in the case of asymptotic safety, you take this point far away from the perturbative domain. Whereas my theory, the way I phrase it, if I have one more adjustable parameter, which is this wire coupling squared parameter, I can take that in the perturbative domain. Then everything can be handled in perturbation theory and just see what happens. Everything should be calculable, but the price will be that, that you have to make considerable modifications in the standard model, because otherwise the calculations give you conflicting results. So preliminary investigation of the standard model led nowhere. I couldn't make the model work such that in the new formalism all its beta functions cancel, and that it becomes a meaningful theory. That is still too much to ask for. But you do get a prediction that such theories may be constructible in not so distant future. A theory where all parameters which are normally freely adjustable parameters in a standard model, all these freely adjustable parameters are calculable. And that's one of the main messages of this theory, that we shouldn't give up hope of being able to compute literally everything in a future theory of everything. And those are my conclusions. The indefinite metric problem can be addressed. The question is, the question is whether what I said so far is a good starting point to understand negative metric problems with this theory. I think it might be. It's something you have to investigate further. So this is more or less a little over my scheduled time, but I also saw that will be plenty of time for discussions. So thank you very much.